All right, so here's another one. How many grams of AgCl will form by adding enough AgNO3 to react with 1,500 milliliters of this? Okay, so there's a little clue here about how to approach this problem. When we see a volume and the word of, a molarity, of means multiplying, so I think I'm going to start with that. However, I know that 1,500 milliliters is not going to multiply directly with moles per liter because the units aren't the same. So I'll convert this by, I can just do this in the same kind of line. I'm going to put the conversion between milliliters and liters to cancel mils, and that means the liters will cancel. So we go 1,500 times 0.4 times 1,000. Now if this is, divided by 1,000. So if it's harder for you to think about this as multiple steps at once, then you can always do the milliliter to liter conversion first and then worry about the rest later. Oops, that's moles. We have 3 significant figures here actually, so let me just clean that up. It should be 0.600 liters because there's 3 significant figures here. Okay, so if I know, not liters, gosh, moles. Sorry, guys. Moles. Okay. Liters canceled, see? So I know that's not it. So we want to know how many grams of silver chloride will form if I have, I have 0.600 moles of AgNO3. Okay, so I can use that molar ratio trick again. They give me the balanced reaction, so I know that there's 2 AgNO3 for every 2 AgCl. So it's not going to change anything mathematically, but you still have to show this. It's almost always worth an entire point just for showing your work there. And basically what we're doing is converting from AgNO3 to AgCl. And then it wants to know grams of AgCl, so then I have to look up the molar mass and go from grams of that into moles. Oh, sorry, this is already moles. I need to go from moles to grams. So it's going to be per 1 mole. Okay, so I went and added it up from the periodic table, and it's 143.32 grams for every mole. Moles are going to cancel here. And our final answer I'm going to put in is 0.6 times that mass, 143.32. And we get 85.99. It's only 3 sig figs though, so 86.0 grams. Let's do that better. Okay, so the last section of this chapter is about colligative properties. It's a fancy word that just means a physical property where it doesn't matter what you're dissolving, it just matters how many particles you put in. So in other words, if I put in 10 particles of sugar or 10 particles of sodium ion, whatever it is, it has the same effect regardless of which substance I'm using. So the 4 colligative properties we're going to look at are called vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. All right, and so vapor pressure lowering happens because when you make a solution, the intermolecular forces of the solution are stronger than the intermolecular forces of the solvent. So that means that the solution wants to stay in the liquid phase and not become a gas, which would mean the vapor pressure is lower. Vapor pressure, again, is the amount of pressure exerted by the gas particles over a liquid. Okay, and so basically what it means is our definition of a solution is that it only forms if intermolecular forces of the solution are stronger than the solvent was. And if that's true, then the mixture doesn't want to be in the gas phase as much as the solvent did. So vapor pressure goes down. There's less gas in a solution than there was the solvent. There's no calculations for that. It's just something we have to realize happens. So if I'm comparing like water and sugar water, the sugar water is going to have lower vapor pressure because it has something dissolved in it. Okay. Molality is a calculation we're going to use when we're talking about the next two. So boiling point and freezing point. Both are sort of quantified by thinking about molality, which was the last concentration unit that we looked at on that chart. It's the only one where the bottom of the fraction is just the solvent. And the reason for that is because it's only used for colligative properties. So we don't need to know about the solution in the bottom. We're just interested in how much solvent there is present. So here's an example. Molality, oh, by the way, it uses little lowercase m here. But the molality, what is the molality of a solution prepared by dissolving 2.7 grams of methanol? So 2.7 grams of this CH3OH. I'm going to have to calculate a molar mass for that. So it's going to be 12.01 for the carbon, plus I have 4 total hydrogens and 1 oxygen. These are all grams per mole, of course. And so we're going to just add those up. So the molar mass ends up being, we're going to put moles on top because we're trying to figure that out, and the grams on the bottom, like so. And so I take 2.7 divided by 32.05 to figure out the number of moles of solute. So that's the top of our equation here. Our equation says moles of solute divided by kilograms of solvent. And so we got 25 grams of water. Water is our solvent here. I want to convert that to kilograms, so I have to remember that there's 1,000 grams in a kilogram. That goes way back to chapter 2, but it is a fact that we need to remember. Again, my significant figures here, this 0 is significant because it's after the decimal, so I keep it. And then I just take moles per kilogram of water, and I'm done. So 0.0842 divided by 0.025. And it says the answer is 3.368, and I'm going to use the little m, but there's only 3 sig figs, so we're going to pick letter C here. Now, molality is used in colligative properties to figure out what the change in temperature is whenever you freeze a solution or when you boil it. So delta T means change. I is called the Van't Hoff factor. Van't Hoff factor. It literally just means how many particles are formed when you dissolve the substance into the water or whatever solvent. M is molality, as we just used, and K is just a constant that depends on whether you're doing water or some other substance and whether you're freezing it. So like the KF here is for water is 1.86, and it has these funny units right here, but we need to keep track of those because it helps us to make sure we've done the calculation correctly. Like if I end up with moles in my change in temperature, I know that's wrong because temperature is just Celsius. Okay, if I'm boiling, we're going to use this constant for water. Okay, so it's important to pay attention to which process we're doing. So boiling point elevation problem. It says, what is the boiling point of a solution paired by dissolving 0.1 moles of sugar? Okay, so sometimes they might have given us grams and then I have to calculate moles, but this time they gave us moles already. So I'm just going to plug that into our formula for molality because I know I need it. And then they give us 0.050 kilograms of water. So they've already kind of done the conversions for us in this problem. So 0.1 divided by 0.5 is going to be 0.2 molality. Okay, so that's step 1, figure out the molality. Then I'm going to plug everything into that equation that we just looked at. So the change in temperature equals, I. Okay, so sugar is a covalent compound, which means like what we saw in the beginning of the lecture here, when it dissolves, it only forms one particle. So for covalent compounds, I value is always 1. So we're going to go 1 times the molality. You know, I actually think writing it as moles per kilogram is probably better. More information is always good. And then this is boiling, so we're going to use KB, which is 0.512 degrees C. And it says per M here, but the prior slide listed it like this. Either way is fine. But this means kilograms is going to cancel and moles is going to cancel, and that leaves us with just degrees Celsius. All right, so we go 1 times 0.2 times 0.512. And we get a change in temperature of 0.102 degrees Celsius. Now, so this is water being boiled, and it says here that water boils at 100 degrees. And we want to know the actual change. We want to take that change in temperature and figure out what the actual boiling point is going to be, because it asks us for boiling point, not for the change in the boiling point. So if it starts at 100 degrees, it's elevated, so that means I'm going to add the delta T. So our final boiling point is just a little bit higher than the pure solvent. Okay, so that's boiling point elevation. We add because it's elevated. Okay. So another example, what is the boiling point of an aqueous solution that is 4 molality? And they give us the boiling point and the KB. So we're going to assume that the I value is 1. They don't give us what the substance is, but if it wasn't 1, then they would tell us. So we could just go delta T equals 1 times 4 times 0.512. And so we end up with 2.04 as our delta T. Oh, sorry, 2.05 is what I got. Degrees Celsius. And that's not the boiling point, though. The boiling point is always added. So we get 102.5 degrees Celsius. So be careful that you didn't pick D. It's very tricky, and they will do that to you on your final, so pay attention. Freezing point is very similar. We're going to use the same equation. Our freezing point is low, it's 0, and our constant is different, but pretty much everything else is the same. So we have 100 grams of this stuff, C2H6O2. That's a covalent compound, so I know the I is going to be 1. I know I'm going to have to figure out molality, so we're going to have to add up these elements. So it's going to be 12.01 times 2 plus, let's see, 6 waters, so that's, or hydrogen, 6 times 1.01 plus 2 times 16. So that gives us 62.08 grams. So if we're starting with 100 grams, that's going to be equal to 1.61 moles. Okay, and it says we're dissolving it into 200 grams of water. So 200 grams, and I'm going to convert it to kilograms. Okay, so our molality here is going to be 1.61 moles divided by 0.2 kilos. So 8.05. So the delta T is going to be 1 times 8.05 times, that's degrees C. Nope, sorry, that's not. That's moles per kilogram. Times 1.86. So our molality cancels, and we get delta T equal to 14.97 degrees Celsius. I have to take that and subtract it from the freezing point initially. So 0 minus 14.97 gives us negative 15. Okay, so that's colligative properties.